Question 2. How much higher must your blood pressure get to compensate for a 5% narrowing of your blood vessels? The pressure difference across your blood vessels is essentially equal to your blood pressure. This question is about Poiseuille's law. Poiseuille's law says volume per unit time is equal to pi times your pressure change, so pi, I guess because it's a circular vessel or assumed to be, times d to the power 4 and over 128 times the length of the vessel times the viscosity of the fluid flowing through it. And this question asks us about blood vessels. It says if your blood vessel gets 5% thinner, what does that do to the change in pressure? And we're going to assume for this that the volume of blood per unit time that you need getting down to your extremities is the same, because if it isn't, your fingers fall off and it all gets all a bit unhealthy. So this is constant, pi 128, length of your pipe is constant. So we've got eta, the viscosity of the fluid, is constant. We've got two things that are going to vary. This one we know has changed, this one we know has changed, that one's how does it respond? So everything else is constant, and actually this is what I'm going to start off by saying is we've got two states of this blood vessel. So we have got delta P for a healthy blood vessel, and that is equal to V upon T times 128 length times eta divided by pi d to the power 4. And then we've got delta P for a tight blood vessel, and that's equal to V times 128 times L times eta over T times pi, but this time 0.95 D, 5% thinner, all to the power 4. And this is a really nasty equation. But we've just said, actually, it's all constants all the way through. My pen is about to fall off the table. So I'm going to do a big fat cheat here. I'm going to say that all of this stuff here and all of this stuff here are essentially the same thing. And I'm going to say that K, is that going to show up? K is equal to 128 VL eta over pi t. And then I can rewrite these two equations in a slightly more civilised manner, especially if I rescue my pen. So we get delta P healthy. This is a bit of a mess of a board. I'm not going to go over there and do this. I will press on down the page, but I might end up running out of space, so I'll do a line there. Delta P healthy is equal to K upon D to the power 4, and delta P tight is equal to K over 0.95 D to the power 4. And I can separate this thing out a bit because it's a straight multiplication, and I can write delta P tight is equal to K over 0.945 to the power 4 times D to the power 4. And lo and behold, that bit there, D over, is K over D to the power 4, is suspiciously like delta P healthy. So we can say delta P tight is delta P healthy divided by 0.851. So it's a fraction of the healthy. The healthy blood pressure is a fraction of the tight blood pressure. But we don't normally, you wouldn't normally write this as delta P tight is equal to 1 over 0.851 times delta P healthy, which is what we've got here. So I'm going to work out this reciprocal to get my neat answer and say delta P tight is equal to 1. Oh, actually this is a lie. This should be 815 and this should be 15. I have a typo. 1.23 times the delta P healthy. So we've got a 5% change in the thickness of our arteries, the diameter of our arteries, and it's introduced a 23% change in blood vessel pressure. And this is why narrowing of your arteries, or any pipe work actually, has a really profound effect on either pressures or flow rates, and both of those are a bit unhealthy if it's blood you're dealing with. Okay, thank you.